Maybe a little warning. This is going to be much talk and much less about Python. If you want to learn about AWS, don't feel shy. So yeah, I'm going to talk about something called research data management, and I will explain what it is, what I mean by research. So as Nai said, I am an MRI physicist, and I worked in a bunch of places, mostly in hospitals and departments of radiology. I studied physics, but I went into medical imaging, so I don't really know who am I, who physicist or neuroscientist. I'm definitely not a manager. As Markus said, actually, when we study physics, we are not trained to become programmers, but it's mostly a need to learn how to program. You cannot be a scientist without programming. So yeah, out of all my name cards, my Hackerspace name card is so far the most successful. Okay, so have you heard about, all developers should know things like test-driven development, behavior-driven development, right? If you've been here 2 years ago and heard Jacob talk on Django, you've heard about something called documentation-driven development. These are techniques that help developers write better code and also write better code not just for themselves but for other people. And documentation-driven development forces you to think much more about your APIs on a much larger scale. Now, a few months ago, I was reading this talk by Kenneth Reitz. Anybody knows? Yeah, the request guy. Problem-driven development. Right? It's a new buzzword. If you want to focus on something, actually, why do you do what you do? This is the question to ask. So I'm very much interested in a topic on open science and reproducible research, especially in the context of academic research. And when people talk about open science, it usually means three things. It's access to publications, it's access to the code which allows you to do your analysis, and access to data. And it's recently started to get more and more attention in many, in fields which are other than physics. Actually, in particle physics and fundamental science, people do collaborate much more than it happens currently in other fields. It's a cultural artifact, but it's like this. So I'm particularly interested in data. And since we're talking about big data, so have you heard about CERN and Large Hadron Collider? It's so this is the biggest scientific instrument currently built or operational. It's only 120 kilometers in length, and it's the biggest microscope. And if you know nothing about LHC, but if you do web development, well, they are responsible for what you're doing. Now, people know about LHC. People don't know what people do in LHC, especially in terms of computing. So building LHC took more than 15 years of planning. And 15 years ago, they already figured out, actually, they all need to do something about computational resources, because this machine produces 25 petabytes of data a year. So 15 years ago, they started thinking, and already 15 years ago, people started building distributed grid systems to handle this. And everything you know about cloud, well, these guys actually built this a long time ago, before it was known cloud. Okay, just a bit of comparison. So YouTube claims they actually have every minute there's 60 hours of video which gets uploaded. So that's roughly 3 petabytes a year. Okay, even if I underestimate by 2, we are still 5 times less than a single instrument in physics produces in terms of data volume. So we have actually these large experiments actually require a lot of investment and time and everything. So these are like really big instruments. But actually, so for each physicist who works at CERN, there are 10 physicists who don't work at CERN and do something else, like Markus, although he does things which are close to what this does. But there are other people, applied science, And for each physicist in general, there are maybe 20 scientists or more that do other things which are equally important. But they use whatever equipment they need to use to do their job. Actually, this is an image on MRI machine. Actually, this is a heavy-duty equipment. It costs $2 million just to buy and $500,000 to operate. It's still expensive toys. So big projects actually do have money and resources to handle the storage and computing power and everything. And usually people understand without professional IT support, you basically can't do what you need to do. In other areas of science, this is not the case. Most people have to rely on their own knowledge to handle their own stuff. And currently, so there are many, many, many more scientists actually doing small research. Not small in terms of impact, but small in terms of funding compared to CERN. And they have to handle everything themselves. So, but storage is not the only problem. So the problem is actually that researchers have to do a lot of things themselves, not just writing code, but actually thinking about infrastructure. How do I archive my data? Where do I put it? Can I retrieve it 3 years later? And it's actually very little help is available at the institutional level because the university's IT department is busy enough with handling emails and PDF files. So for many universities, publication is what they actually care about, and that's what they care. But the problem is for scientists, everything which needs to create a publication handled by themselves. And it's not easy. So I want to quickly show you a type of projects which I was used to be doing. So I don't know, maybe 10 years ago, I was studying this brain variability. Actually, it was an artifact because we were doing something else and we figured out we don't know enough about brain anatomy. So we started doing this. So the image below is basically taking a bunch of healthy subjects, and then you scan the head, then you extract the brain, then you look where the sulci is, and then you try to normalize this and put together, and then you don't know what to do with it. Nice image. Okay, but to get there, this is what we would call a data processing pipeline. So I start with some original data. I do a series of transformation before I arrive to something which I want at the end. So we have this concept of starting with some data, running it through some analysis script and having a final result. Actually, this is not a final result. This is just my result where I can start aggregating my data to do some whatever conclusions I have to make. Just like Marcus is saying, we start with a bunch of data coming of all sorts of sensors, and then you need to aggregate, try to figure out if it's useful or not. So in many areas, actually, some of the steps are easily reproducible, so I don't need to save them. But if this thing takes me, let's say, half a day of processing time, I have to save this. And I have to know from where it came before. This is what we call data provenance management. Like, where did you start to arrive to your result? And this is really hard. Currently, technically, there are no tools I know of. So there's this problem of data organization. This small science, most of it is put things on a USB drive into a file structure and try to stick to a naming convention and hope for the best. So we started with an original project which actually had nothing to do with anatomy and had everything to do with functional MRI of the language and how to localize it in the brain and how do you want to compare it across several people. And then we tried to basically, the standard approach is to use a template, and it's like almost coordinate-based system. And we thought, actually, why can't we attach an activation to an anatomical landmark? That's when we started thinking, oh, there's an interesting anatomical variability problem. And at that time, we figured out the best human anatomy atlas published in medical literature was based on 30 brains. This is 3.0. This was only 10 years ago. I hope things have improved since then. So we'll start with one project. Then I have to actually clone it, make it into another project. So in the original project, I would actually organize my data into like subfolders. I know my raw data, whatever is coming out of the equipment, it's in some format. But so there's this format called DICOM, and all scientists, as soon as they see DICOM, the first thing they do, they will convert it to something more useful, because it's just so hard to use and not so easy. So we converted, actually exactly same data, just represented in a different way. So you have multiple files which represent the same, what we call an image sequence. It could be 2D, 3D, 4D, or whatever object. And you just need to know, you have to keep track of like what was the experimental settings, in which order things were acquired, where is my top of the head, things like this, where's left and right. So you need to keep a track of some kind of meta information about what you're trying to do. So this is the original project. Now I want to switch to do this anatomy project, and for that I need to maybe use a different tool, and a different tool would probably ask me to do a different layout of my files. So I need to reorganize things a little bit, maybe rename them, just to adapt to whatever tools you have to use to get to your point. So that's a bit of a problem of data organization. So even if you have like decent computer skills, you know how to use find, and you know how to pipe it into several commands. And actually many scientists don't, because it's a bit boring to learn the terminal. But even this is actually not useful, because a lot of this metadata is saved inside these binary headers. And standard Unix tools, this is pure text. It's really hard. So what's the problem? 10 years later, I cannot redo what I used to be doing. I actually still have my data, but it's on a CD-ROM. I don't have a CD-ROM writer. Actually, practical problem. Now, the actual problem is that actually there are no simple tool for handling collections of large binary objects. That's the gist of the problem as I see it. So what this tool basically we need a tool that will help us a bit with data organization, just propose a more sane structure. It will help me track my notes. Where did I do the data? What did I do to the data? Some comments, whatever. I need to track data provenance, and I need to be able to search beyond file name and create modify time. And I also would like to have a good sync between local, remote, and maybe my hard drive and whatever remote storage I have to. So actually I'm not the first one to talk about this. Actually, there are quite a few projects that try to attempt this. I mean, CERN obviously solved the problem. So WLC, this is the LHC computing grid website. So they have to handle this, so it must be solved. There are national level well-funded projects, both in Europe and in US, that try to address this problem. Then there are like some very specific projects, let's say for guys who do optical microscopy, they have tools already made for them. So why am I talking about things which have been solved? So the problem with national level project is actually too big, and actually most, again, IT departments, they don't have time to connect things and make it happen at a university for some reason. But for specialized tools, like this tool, open microscopy environment, tool exists. It's a desktop application. It's a web application. There's a database backend. It's basically a LAMP stack. So the problem is this, right? Scientists, they don't want to handle this. And the IT department will never, what is this Omero thing, right? So you have to, it's like telling all the non-tech people to run a WordPress blog on their own. I mean, people would rather just use a hosted solution or whatnot. But there are constraints in academia or elsewhere that you basically have to run local resources. Either it's IP issues or whatever. So, and it's not happening. It's really, really hard. And again, scientists, they are not programmers. They are even less sysadmins. So, so another problem which is actually so bad in science is that, so this is the equivalent of OMERO, the microscopy for managing MRI images. Okay, this is not sexy. So one big problem it's hard enough to hire an engineer for your academic project to do development. It's impossible to hire a graphics designer or usability expert. People who actually maybe have the best chance with modern technologies are guys from Open Knowledge Foundation. If we have time, I'll show you the websites. But they focus on open government data, like opening up statistics on a national level, on a municipal level, this kind of things. They open on like economics data, more like high social impact. They don't provide tools for, let's say, a molecular biologist to handle his data. Well, some other people have solved this problem, right? Amazon handles images. These images, the operating system, like virtual machines. Each virtual machine is what, 4 gigabytes, 8 gigabytes of binary blob. You need to manage this. iTunes does this. I mean, everybody using some tool to handle their music and video. And it's a similar problem in some way, except that this is a much better understood domain because the data organization is already known. It's an album, it's a track of an artist. So there's much less variability in what you need to keep track of. So in comparison, a scientific experiment would basically, you need to track about maybe 300 parameters and you don't know what they're called. I mean, if I'm a developer, I don't know what makes sense to a molecular biologist, what is important to him and how to call it. So there are no settled vocabularies to make it in an easy way. But management of software packages, this is becoming, it used to be a pain, but it's improving. So Debian, deb packages, RPM packages, and even in Python, creating a package for distribution for installation, it's also a problem, which is now being solved with distutils and things like this. So Node people are doing something interesting. So how does it work? So very simple. It's a simple text file with a few agreed fields. Actually, no committee ever said, let's structure it in this way. Just put a few sensible names into your text file and describe your data, right? Who was the author, a bit of description, the version number, where you get it from, a little bit of some keywords. So with this, actually, it's a minimum amount of infrastructure that helps you build a software distribution package system. So this is an example of a JSON package for Node people. So again, it's the same thing, except it is done in a JSON format. And the really good thing about this is actually it's independent. It's language independent. All languages now have this. This is becoming the lingua franca to talk about exchange information online. So I spent actually some time thinking about this, and I was thinking, yeah, I have to learn about databases and all this MongoDB things. But actually it happens that actually even the same people, the Open Knowledge Foundation people, they've started a project called the Data Package already some time ago, but I think it's a very slow development project. So started in 2007, it's 5 years later, it's still, nobody knows about this, and the GitHub hasn't been updated in the last 2 years, I think. But basically it's the same idea as the package JSON. Put a few sensible text fields inside, do something about this. Now I think YAML is even better for this, I think, because this is much more human friendly because there is so much variability in terms of type of fields we want to cover and experimental condition and whatnot. It has to be very, very free and fluid, in addition to actually having a few items of control vocabulary. So basically, in any experiment, we have 3 levels of things to keep track of. General project, then the experiment that happened at one day, and then the actual acquisition that happened during the experiment, maybe, or it's like called a run. I start an experiment and I use a few runs, and then that's actually my single kind of chunk of data. So what the hell is that? Okay, Dacets is a name I came up with. I'll explain later. So this is how I would like. This is like a really early prototype stage currently. So it's a kind of like command line tool that allows me to import some data into a project, add some files into a project. I can remove stuff, and then I can do like a find based on a few keywords. And I can generate a Dacets JSON file, which is basically a list of data package files plus a few meta information that basically puts a collection of objects into a single file. And I can use it later to either do a sync or whatever, or I can do some statistics on it if I want to search inside this, like subsets of data inside this. And I would like to do the same from Python. So I can basically load the same JSON and do something. Let's say I can quickly load my data or do a similar search. And then I can feed this to my pipeline script that basically will do my full experiment. Okay? So that's the way I see it now. So currently Dacets stands for, it's a datasets plus facets. Facets comes from the faceted search kind of things. It's just a collection of related keywords that make sense to describe a specific data set. And it's a kind of, I look at it as a binary file version control system. I don't want to handle the actual binary file themselves. I just want to handle the link to the file and all the meta information. And it's a free format, majorly. And I really want to have it as a module and be integrated in a notebook, IPython notebook, because Notebook has one thing which is really powerful. This is this new display environment where you can attach a rich representation for an object. So when I say show me a dataset, I will have just maybe a graphical representation or a graph or an image associated to it, and not just from which project it's coming from. So actually, some people are doing things in this direction. There is this project called Git Annex, if somebody heard. It is a Git extension which is actually completely unrelated to Git. It's written in Haskell to manage your media collection of videos and I think photos and music. Mercurial also has an extension called Large File Extension. This is similar to Annex. And then there is this very new project called Sumatra from France. This is an environment built on top of Django that helps people who do actually brain simulation, like at the cellular level, to control their experimental runs. Like I want to simulate a collection of cells and their firing pattern. So I have my simulator and just a file which describes a bunch of parameters. And then when I run it, actually it logs exactly the command that was run. So I can exactly repeat what was done. Because people have sort of, you do your simulation, tomorrow you forgot why you did the simulation. That happens all the time. And again, so this project in Open Knowledge Foundation called Data Package Manager. So, but this seems to be a little bit abandoned currently. But again, when I look a little bit into this code, it's still more, so currently they focus on like CSV files and like whatever you would expect from a statistics department. So it's not really meant for handling like large binary objects so far, but it's still something that people are solving this kind of problems in other fields. So that's actually all I have to say. If I have time, I can show you some of the websites of this interesting talks. Yeah, so if there are scientists in the room, you should read about Science Code Manifesto, or this guy. Yeah. Yes.
So why? Okay, so I mean, if it's a custom binary format, don't you have to make it application specific? Like whatever. I mean, like I have to know which binary format it is, kind of.
Yes, but this can be part of your JSON file. It's the problem is actually scientists they usually forget to write a README. Completely free form and just or if they write it and then they copy it over and it's whatever gets lost somewhere. So it's a I don't know.
And what's the challenge with the big binary files? I mean, they typically do not tend to change, do they? So I don't even have to put them on the version.
Well, it depends how big you think is big. So Git is not good at, let's say, if you handle professional photography and your resolution is, I don't know, 10 million or something like this, you don't want to put it under Git because every time you change the file name or do something with the file, the blob will be recommitted.
Do I have to put it under Git because I will never be able to diff it anyway, so I can just...
Actually, people do work on binary diffs currently. There are projects as well. No, I mean, I don't care about my binary, the stream of data sets. I don't want to put this under Git. The only thing I want to do is many files which come out of equipment have this header, which is binary, which is embedded into my file, or it is saved as a header file next to the data file. And this is binary, and this is not searchable. So what we need when I do an import of a project, I have a hook that knows how to parse the binary header and dump it into JSON. And this, I don't need to write this all by myself. This is it's just a hook system. You can attach your own binary to JSON converter for the format that makes sense to you. I don't want to tell you what to do with it. Okay, so these guys are doing some very good job. Open Knowledge Foundation, and that's the SCAN project. This is it's a pyramids-based web app with quite a good and sensible technology behind to handle collections of what they call digital assets. What else? Actually, there is a data hub, which is also run by them. But again, currently this is mostly like economics data set, whatever. But this is still like a good, it's a, how to say, it's in the right direction. And for Sumatra, this is like how it would look for, let's say, a project of a simulation project. So they also have a command line, but they also have a web interface, like the reason for doing the, I like the naming, the reason for doing a simulation. Well, they forgot to put the reason. But so, yeah, it's a simple tool that, again, works with mostly text files which are attached to your specific experiments. And that's, having this would be super useful, I think. And it will help people to share data and make results more reproducible. Yes.
Did you have to get in touch with the machine manufacturers to understand how to parse out the binary? Because presumably these are like custom formats for whatever the machines are, right?
Sometimes yes. Sometimes manufacturers, they want to open it up themselves, because if they keep sitting on the format, they know nobody will use them. So there's also a trend of actually people understand you have to start opening up, otherwise you get ignored. But the problem is, actually we scientists, because we're not good programmers, as Marcus said, we tend to create our own formats. That's a bit of a problem. That's okay. That's when we think we're getting too smart for ourselves. We say, oh, I don't like, for example, in the case of medical imaging, people say, oh, DICOM and its new format, and everybody should learn it and be happy with this. But no, it's over-engineered, and it's basically a, I would say, job security for healthcare IT professionals. So, yeah, so There are different reasons why people prefer to choose a format over the other. Sometimes you have to use a proprietary tool, or you don't want to rewrite another tool. Even if it's in MATLAB, you still don't want to change it. And this tool requires you to change format. So we will never come to agree on a common format in science, I think. I mean, there will be some trends how binary data is represented in memory. But I think we actually shouldn't forget the power of simple text and things like JSON and YAML.
Is Dacets open source?
Yes, but VIP. I still haven't really, I mean, a little bit ashamed to publish it, so. soon, coming soon. Yes, I'm working on this.
For PyCon attendees.
Okay, sign up for the access code. Okay, anymore.
So I'm actually a bit curious. Why is it that, given the importance of, for the university, the amount of money that they spend on research and they value publications, why isn't this trickling down to helping to solve this kind of problem?
I think it's a hard problem, and it's mostly political problem. And yeah, I don't have a really good answer to this. Why is it not happening?
Well, what do you mean, like political? For those that
Well, I mean, academia is like a super resource-constrained environment, and people compete for things which are known that are valuable. So currently, your only currency in academia is your publications. Nothing else is recognized, really. And university administration, they would like to actually encourage and whatnot, but scientists themselves, they say, why should I make this available if only publications are counted? So it's a bit of a...
So actually, like, help bad for them. It helps their competing scientists.
Well, this is still a mindset in many places.
Any more questions?
No, I guess. Can we have a round of applause?